Thank you. Oh, thank you, Wesley. Odd. It's fine. Okay. So 3.2 measurements of position was largely based off of, so thinking about like percentiles, quartiles, all that, largely based off of what we knew about the median. But generally speaking, the median is not going to be our go-to measure of center. Oftentimes, it is going to be better, quote unquote, to use the mean instead. And we said, okay, well, there is a way to communicate. Your questions? There is a way to communicate information about position in regards to the mean. And that is going to be in what is called the z-score. But we didn't really quite have enough context to fully talk about kind of what z-scores are until 3.3, where we were looking at standard deviation in particular, which is going to give us that missing link to allow us to talk about what we actually want to talk about. So what we are going to be focusing on here is a specific type of distribution called the normal distribution. This is a fairly spectacular distribution. I mean, it's the most kind of basic cookie cutter distribution, but it is also, I think, one of the most impressive that you can get. And what is so just absolutely crazy about the normal distribution is that if you collect enough data, every single distribution is going to end up looking like a normal distribution. So given enough data points, you should end up working with something that looks like this, which makes it a very, very useful distribution for understanding kind of general large-scale trends in the data. So this is the distribution. That you get if you have enough data. And in particular, it is characterized by kind of a large amount of data in the center, and then as you taper out from the center, you get less and less and less and less. So the central measure that we are going to be using here is our mu. And in particular, the way that we move away from mu is going to be with what we covered on Friday. We're going to be moving away from the center in terms of number of standard deviations. So for instance, this first line on the right here is going to be 1 standard deviation to the right. The second line here will be 2 standard deviations to the right. The third line here, 3 standard deviations to the right. Likewise, 1 standard deviation to the left, 2 standard deviations to the left, 3 standard deviations to the left. And you can have more. It would continue to go and go out. You could have like 6 standard deviations to the right. Whatever. We're going to see by the time we get to 3, we're dealing with so much of our data that it doesn't make a whole lot of sense to talk about what's going on beyond that. We'll mention like, oh, hey, by the way, we can sometimes see data out here. But the data on the outside of 3 standard deviations is fairly rare, as we are going to see. Now we had a rule at the end of Friday, not really a rule, it was a theorem that was used to kind of give us an estimate of how much of our data we would see within a certain number of standard deviations. So for instance, that was the Chebyshev's theorem, which was saying like, hey, if we're within 2 standard deviations of my mean, then I can do like 1 minus 1 over 2 squared to get that I should see at least 75% of my data, regardless of what my distribution looks like. So it could be skewed, it could be symmetric, who knows what, but if I'm 2 standard deviations away from my mean, at least I should have 75% of our data. When we actually know the distribution that we're referring to, we can do better than just saying this is our guess as to how much data we would expect to have. We can be a little bit more refined than that. And so for our standard distribution, we're not really going to use Chebyshev's. That's a good tool when we don't know the shape of our distribution. But standard normal distribution, we do know its shape. And so the rule of thumb that we are going to follow for the amount of data that we will see within a certain number of standard deviations is the 68, 96, 99.7 rule of thumb. You'll sometimes see it as 95, but technically speaking, the z-score for 95 is 1.96, and the z-score for 96 is like 2.001, or like it's closer to 96 than it is to 95. The exact value at 2 standard deviations is around 95.96 of your like percent of your data or something like that, or maybe it's like 95.6. It's a little bit more than 95. But sure, yeah, sometimes you'll see this as the 95 rule. I just prefer it as the 96 rule because 2 standard deviations is not used for the 96 percentile, which is important, or for confidence intervals. All right, and essentially all this is going to give us is the amount of area that we see within 2 standard deviations. So for instance, if I am between the -1 and the +1, so within 1 standard deviation of my data, then I would expect this total area to add up to this first value here. This should be about 68% of my data. Likewise, by the time I get to my second standard deviation, yes, sometimes you'll see this as 95. I'm calling it 96. We should have about 96% of our data trapped between these values. Yeah, I guess it's like 95.6 rule if we want to know, if we want to memorize to the decimal, but you can think of it as 95, you can think of it as 96, either way. So this would be 96%, somewhere between 95 and 96% of our data. Now we can do a little bit more of a delineated breakdown than that. So for instance, we should have, for this normal distribution, we've got a symmetric distribution. We'd expect similar amounts of data to the left and to the right of the mean. So if between my -1 standard deviations away and +1 standard deviations away, I see 68%, how much percent of my data should I see between -1 standard deviations and my mean itself? So for this bucket here, how much data should I see? 34%. And in my kind of same bucket, we should see 34 on the other side as well. You'll sometimes see the next is like 13.5 or 14, depending on whether we're doing the 95 or the 96. I'm going to go ahead and call it 14. Again, it's like 95.6, but whatever. And then here we have about 1.85%. And then on the outside tail, we've got 0.3% left over. And so for each tail, we've got about 0.15% to the right of 3 standard deviations and 0.15% to the left of 3 standard deviations. So very, 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 very little data once we get outside of that kind of 3 standard deviation metric. All right. So let's take a look at how we can we have this very, very generic setup. Let's actually take this and convert it into something a little bit more specific. Like let's put some actual numbers to this. So looking at our second example here, we are asked to draw and label the normal distribution given a particular value of mu and a particular standard deviation. What am I going to use my value of mu for? Where does mu go? In the middle. So this is 12,494. Okay. And then how could I figure out what's going on to the right of mu? How could I figure out what's going on to the left of mu? Every time I move over a tick, what am I going to do? Plus or minus up or down the standard deviation. All right, so if I want to figure out what comes next, we could, in this case, think about like adding that 1290 to get 13,784. And just going through and adding it over and over and over again, right? So then 15,074. 15. And lastly, 16,364. And likewise, to the left, rather than adding, we're going to subtract. So this should be 11,204, and then 9,914, and then 8,624. Right, but again, just think this is mu, and then we are moving out like 1 standard deviation, 2 standard deviations, 3 standard deviations, moving back 1, back 2, back 3. Okay, so we are asked then to come up with a few percentages. For instance, trying to figure out what percentage of vehicles drove less than 11,204 miles here. So if we're looking less than that particular value, which side of that number should we look at? Are we looking at everything that falls to the right or to the left? Everything to the left. So we're looking at all of this data here.
But you can't go into negative, right?
Yeah, so you wouldn't be able to, we definitely would expect to see all of our data by the time that we have, by the time we hit 0, we would expect to see 100% of our data. Yeah. But it is interesting to note, like, there is no point at which mathematically we would say like, oh, we're definitely out of data here. Like I could go like 1,000 standard deviations to the right, and I can't conclusively say that there's absolutely no data points all the way out there. But we can, for this particular case, definitely say like, oh, at some point we're going to hit 0, and that's going to be our point of no return. Okay. So what could I do in order to figure out what percentage this area of my graph makes up? What would I need to do here? So we know that the big one here is that 34, but what was the next one? The 14, and then was the the 1.85 and then the 0.15. How much does, well, we can just go ahead, 1.85 and then 5. So say again? So we don't even need to do all of that. We just need to add all of these. 1.85 plus 0.15, adding them all together, and we get that we should have 16% of our data to the left of this. Which should hopefully make sense, right? We have 34% of our data under that one curve, and then we have like, what, 50% of our data over here to the right of our mean. So 34 plus 50, we've used up 84% of our data. That's 16 left over to be to the left of this value. But just very simply adding up the percentage contribution of each little bucket here. All right. We're also tasked with finding the percentage of vehicles that drove less than this 15,000 mark. So everything to the left of what we see here. What could I do in order to figure this out? Yeah, we could just go through the exact same process, summing up everything that we needed. That's not a bad idea. That will certainly work. Is there any way that we could do that maybe more efficiently? Yeah, we could do like taking that 50% that we, yeah, so we have like the 50% to the left of the mean. We know that we're going to cover all of that, and then maybe add those next two buckets. That would certainly work as well. Anything else we could do? I like all of these ideas so far.
Well, you can just do 100 minus 0.85 and minus 0.
Yeah. So we could go through and add up everything together, and there are like quick ways, nice quick ways to do that. For instance, like thinking of like, oh, I have all this left 50%, that would totally work. But also to Merrick's point, we know that this right here is 1.85 plus 0.15 is 2%. And so we have everything except for this 2%, which means how much of our data does this cover? 98%. Okay. What percentage of vehicles drove more than the average? 50%, right? We're just saying everything that's to the right of our curve. Everything to the right here. Absolutely, 50% should fall to the right there, 50% to the left. And then we're being asked to figure out how much should fall between 9,914 and 1,378. Yeah, very good. So again, we could just like add up all the buckets and that would be totally fine. But we could also think about taking like the 68% that we get between plus and minus 1 standard deviation and maybe like adding it with the 14%. And we should see that this is in fact 14 plus 68 gives us 82%. All right, questions with this first example? Okay. So this is going to give us a framework that will allow us to talk about position relative to the mean. The actual value that we are going to put to that, the word that we are going to put to that is what is called the z-score. Very, very simply, the z-score is the number of standard deviations a value is from the mean. So for instance, if our z-score equals 1, then that means that our value is 1 standard deviation from the mean. And because it's positive 1, we'll say that it is also to the right of the mean. It's going to be larger than the mean. A z-score of 2 would be 2 standard deviations from the mean. Z-score of 1.63 is 1 full standard deviation, and then 63% of a standard deviation on top of that from the mean. For our purposes, we are going to be rounding these to the hundredths, or to 2 decimal places. Actually do the rounding. And this is kind of the reason why I kind of don't love saying the 95 rule, is because technically the z-score that goes with covering 95% of your normal distribution is plus or minus 1.96 rather than 2. And so the rule doesn't quite work. It almost works, but it's just a little bit off. But we'll look at that later. That'll be a thing that we talk about later. There is a formula for this. We are going to come back to that formula. I want to do this intuitively first, and then I want to show you guys that the formula, in fact, is doing exactly what we are saying that it is doing. So let's take a look at this example here. We are trying to give in a normal distribution, assuming we have enough points to have a normal distribution, given this mean, given the standard deviation. We're trying to figure out the z-scores for these particular point values, for these particular scores. All right, so let's try this. So starting at 18, I'm trying to find the number of standard deviations that 5 is from 18. What would 1 standard deviation to the left of 18 be? 1 standard deviation? 14. So this would be minus 1 sigma. What would 2 standard deviations to the left be? 10. This would be minus 2 sigma. What would 3 be? 6. And then 4 would be 2. So this is. Okay. So just kind of intuitively, where is our standard or how many standard deviations-ish is 5 points away from our mean? Yeah, so about how many standard deviations do we see? Just ish, approximately. For 5 points, yeah. So where does it fall? Where does 5 points fall in this range here? To the left of 5 points would be right here, right?
Oh, I understand.
Well, we don't know whether the mean is an actual value that we score. You're never going to have one exact like value occupying percentage. We generally say like from a value to another value. But we think of the mean as representing 0 standard deviations. Like a number is 0 from itself. So notice that our standard deviation that we're given is 4. And so each kind of notch that we're moving out is spaced apart by 4. And the question is, where is 5? Where does 5 sit? Notice that 5 is... Okay. So 5 points is the value that we are actually, measuring. Yeah. Do we have questions? Okay, so how many standard deviations do we have here? About -3 and maybe a little bit more than -3, like somewhere between -3 and -4 standard deviations. But it's not exact, right? It's not -3 standard deviations. Okay, so let's make it a little bit more exact. What's the difference between -3 standard deviations and the value that we're actually seeing? Just 1, right? We're 1 away from being at -3 standard deviations. So what percent difference do we see between having just 3 standard deviations and kind of like our next standard deviation? How much more do we have? What's like the excess? 1 point out of 4 to make up 1 standard deviation, right? 3 full standard deviations, and then 1 of the 4 points that we need for the next standard deviation, which gives us a total of -3.25 standard deviations, right? 3 full standard deviations, and then a 4th of another. It'll depend. It'll depend. So like, for instance, notice that when the numbers were a lot larger for like this example, our standard deviation was a lot larger, and it would be harder to do something like this. Okay, so the numbers here are fairly nice. This isn't too difficult to work with, but to Liz's question, what if the numbers weren't nice? What if we were trying to do this with the previous example that we had? We do have a formula that communicates this exact same information, right? We're essentially trying to take the distance between our standard deviation, or not our standard, our mean and our value, and divide it into a number of standard deviations. The way that we can do that mathematically is we can say that z is equal to my value minus the mean divided by the standard deviation, and that accomplishes the same thing. Right? This is telling us the number of standard deviations. In particular, the distance between 18 and 5, I have to go 13 to the left. Well, each standard deviation I get when I travel 4, and so the number of standard deviations that I see traveling 13 to the left is -3.25, which is -13 divided by 4. This is 5 minus 18 divided by 4, which gives us as well this -3.25. Okay, so let's see if we can do this intuitively first, and then let's see if the formula in fact confirms what we're seeing. So for 21 points, what would so that's more than our mean, what would 1 standard deviation to the right be? What? To the right of 18 plus 4? 22 plus. Yeah, you're good.
Are we doing 21 points?
Yeah, so we're looking at 21 points. Where does 21 points fall? So in between these, we're going to find 21 points. What fraction of a standard deviation do we see here? Of 4 points, we are 3/4 of the way to our next full standard deviation. So what we have is 0 full standard deviations and 3/4 of a full standard deviation to the right. That z-score should be 0.75. All right, 3/4 of a standard deviation is what we are seeing. And when we do that calculation, 21 minus 18 divided by 4, you in fact do get that this is positive 0.75. All right, where would we expect 12 to be? Perfectly in the middle of 10 and 14. So what should the z-score be? Negative 1.5. In between -1 and -2, halfway in between. And in fact, what we get when we do 12 minus 18 over 4, -6 over 4, which is in fact negative 1.5. Okay. I wanted you to see what it is that we are doing kind of conceptually. We're going to use the formula is really what it is. You're just finding that distance between your value and the mean, and then you're dividing it by the standard deviation, chopping it into number of standard deviations. Right? It's like the same thing that you would do if you were trying to subdivide anything into a different denominator. All right. Questions here with finding the z-score from a value. We can also do the opposite. All right. We can be given a z-score and use it to calculate the value that it corresponds to. You could actually solve for value from this equation, and that would work. But we can also figure this out relatively intuitively. If I have a z-score of 1.3, am I scoring above the mean or below? Above or to the right of the mean. So I'm going to add on whatever I see there to the mean. Cool. And then what does that 1.3 represent? Number of standard deviations. So if I have 1.3 standard deviations, then 1.3 times the standard deviation gives me the number of points above the mean. Which I can add to the mean to get that this would come from a score of 93 point, I think it's like 36 or something. 93.63.
So once you do that time, if you do that, it'll equal 6.63, and then you just add it.
And then you're just adding that to 87, exactly. So for instance, a z-score of negative 0.2, is that going to be a little bit above the mean or a little bit below the mean? A little bit below. And so we would take that negative 0.2, a little bit below the mean. How much below? A little bit more than a point below.
It'll be 5.9. Well, yeah,
Something like that. So ever so slightly below.
thank you.
All right, questions here with z-score. We'll do some practice on this tomorrow. Couple of reminders about tomorrow. So tomorrow is our review day for the tests that we have on Wednesday. If you guys have questions, that is the perfect time to ask them. I will also be here tomorrow afternoon until 3:45 for my tutoring. So if you have questions that you don't get addressed during class, you're more than welcome to stop by then. But do come in with questions. I am going to spend the judge time. If you guys have questions, answer your questions. So if you have questions, fill that time a little bit more. Beyond that, have a good rest of your day.
Am I taking this tomorrow, like, first thing?
Yeah, that's what I was figuring we'd do. Because we'll technically have